Welcome everyone. So this is the last, now we are starting the last 3 lectures of this course. I thought that now basically we'll go into material that's somewhat more advanced. So far I've been talking about stuff that is also been somewhat advanced, but now I'm going to depart from textbook material starting today and go on to material that is only usually found in the research literature. What we'll talk about today will be some additional derivations of Hawking radiation, which we did yesterday. We talked about Hawking radiation and I gave you the simplest motivation for Hawking radiation. Today I want to talk about Hawking's original derivation of Hawking radiation, how he did that. And the reason for that is that it brings out the original intuitions, and it's also useful because it brings out some insight into what is happening in this whole process. And it's insight that's very useful when you think about this process more. And I also want to give you what I think is the most precise derivation of Hawking radiation, which is derived by a consideration of local field correlators in the Schwarzschild black hole background. And neither of these, the Hawking derivation is of course usually, it has been known for a long time, but is not usually presented in textbooks. And the derivation using correlation functions I'm going to tell you now is also something that people in the research community understand, but as far as I know is not presented in textbooks at all. And therefore, I'm going to talk about non-standard stuff, and we'll go a little fast. So you should be. I'll give you references, and the lecture notes will be online. You can look at them. But if you don't follow everything, don't get scared. That's okay. What's important is that you get a feel for what is happening, and you get a sense of what the ideas involved are. So try to get what the main ideas and what the concepts involved are. And if you don't get all the details, that's okay. And it's only reasonable that you'll have to go back and look at this in a lot more detail to get all the details. Okay, so with that, that's just a disclaimer at the start of this lecture. And what I say now will hold more so for tomorrow's lecture and also for day after tomorrow's lecture. And so please keep that in mind. Okay, so with that being said, are there any questions about yesterday, what we did yesterday, which was the derivation of the Unruh effect, and a simple derivation of Hawking radiation by applying the Unruh effect to the black hole horizon and saying that it looked a lot like the Rindler horizon. No questions means everyone has understood, or that no one has understood. Okay, if you haven't understood, the Unruh effect, it's important we can discuss it now. It's because that's something that is rather straightforward. So I'm happy to discuss it now if there are questions about that. Okay, if not, we'll have some more discussion sessions tomorrow and the day after, so you can ask in that. So today what I want to do is I want to consider, Hawking's original derivation of Hawking radiation. If you look at Hawking's paper, which is called Particle Creation in Black Holes from 1975, and the precise references in the lecture notes, which we'll upload at the end of this lecture, then you see that the original derivation he had of Hawking radiation was actually very geometric. It didn't involve the Unruh effect, which was actually discovered after a lot of this understanding of Hawking radiation came into being. And so the original derivation that he had was a very geometric derivation. So let me try and tell you what the idea is, and it's very important that you get what the idea behind this derivation. Okay? So the idea is as follows. So remember the Penrose diagram we had for a collapsing star, which was the Penrose diagram we had for the Oppenheimer-Snyder solution, right? So this is the R equal to 0 line. And this is the surface of the star. Okay. And this is past null infinity. Future null infinity. Right? Now, what does it mean when you say that you have Hawking radiation? What it means to say that you have Hawking radiation is roughly the following process. It says that you start off in a situation where there are no particles coming from past null infinity. Okay, this is the horizon. start off in a situation where there's no particles coming from past null infinity, okay, and you end up in a situation where there are particles going out to future null infinity. Okay, so that's what it means. What it says is that there are no particles that were coming in the far past from infinity. So it was not like you had a lot of radiation that was coming in the past that is now streaming out to the future. But rather that you start by in the past in the vacuum. In the vacuum, of course, and there's this shell which is sitting at past time like infinity. But you start with no radiation in the far past. But what happens is that in the far future, the fact that this geometry is time dependent, it's a time dependent geometry. The fact that this geometry is time dependent leads to the creation of particles in the far future. Okay, so the physics of the Hawking effect is this. It's that you start off with the vacuum in the far past, and you have the shell collapses. As a result of the collapse, the geometry becomes time dependent, and as a result of this, what is the vacuum in the far past is not the vacuum in the far future. And if you start with a vacuum in the far past, an observer who's using observables that are tailored to the far future, to future null infinity, sees a thermal bath of particles. Okay, so this is the physics of the Hawking effect. How do you make that precise? You see, you can expand solutions to the wave equation, the massless wave equation, in terms of Cauchy data on past null infinity, or on Cauchy data on future null infinity and the horizon. Okay, so let me call this N plus. Right? So there are two ways to specify initial data for fields. So initial data can be specified, A data on, okay, this is past null infinity, okay, or okay, so you can specify data for the fields either here, or you can specify data for the fields either here or here. And the statement is, if you specify data for the fields so that things are the vacuum in the far past, then you get a configuration where things are not in the vacuum in future null infinity. Okay, is this clear?
Why are we considering only null infinities, not time infinities?
So we're going to consider massless particles. So massless particles come in from past infinity and end up in future null infinity. Okay, is this clear? Okay, so what does this mean, more mathematically in terms of what we've been talking about in Bogoliubov coefficient? It's the statement that if you have a parameter here, which we call V, okay, and you have a parameter here which you call U, and you have some other parameter here which you can call V plus. Okay, so this is V, U, and some V plus. Then the statement is that you can specify, decomposition of the modes of the field, okay, as phi is equal to sum, okay, AI into some modes which have the property that as they go to there's one phi AI. And this expansion, right now I haven't written anything, it's just some expansion in modes, has the property that as you go to past null infinity, on this sky minus, this becomes a plane wave expansion on sky minus, right? Of course, by R, there's always an R that enters these spherical waves. Okay. So you can specify data for the fields by specifying ingoing particles coming in at past null infinity. So there's one expansion for the field that basically says you have some particles they're coming in at from past null infinity, and so that tells you that they have some oscillations here. Okay, and you can specify what those oscillations are. Okay, is this good? Okay.
This is not a vacuum state you're taking, right? It's
This is just an expansion for a field. There's no state.
okay.
Right now there's no state. It's just an expansion. There's another expansion you can write down, which is an expansion of the fields on future null infinity. Okay, so let me call this phi past. Then there's another expansion you can write down phi future, which looks like sum of, bi, gi plus some ci, hi plus summation conjugate, where these bi, gis, in these modes, the ones which I'm calling di, have the property that goes like e to the I. Oh, sorry, maybe I should put minus. So this expansion, this part of the expansion, which is this part, is part that leads to oscillations on future null infinity, and there's one more part that leads to oscillations on this horizon that we are not going to be so interested in. So these modes, we are not going to be so interested in the CIs.
So
Yeah.
Will
Yeah, go on.
there be any problems because we are considering a vacuum solution and a field?
There was this collapsing shell nulling past null infinity.
That's
Does
it.
that affect the modes?
Does it affect which mode?
The past infinity modes?
There's a collapsing shell which is at past infinity. That collapsing shell is, it's something which is coming in from past null infinity. That doesn't affect, what's happening at past null infinity. You see in the Penrose diagram, this is effectively one point on the Penrose diagram. And there's data you can specify on past null infinity, which is, there's an entire fine parameter runs along past null infinity. You can specify data.
So given the fact that we know that the near horizon is similar, does it make sense to assume that CIHI also comes with the Hermitian conjugate?
Oh, CIHI certainly comes with everything comes with the Hermitian conjugate because the field is real. No, everything always comes with the Hermitian conjugate. The Hermitian conjugate is there, it's just saying the field is Hermitian.
Okay.
So that, whenever you write down expansion this kind, you always write down a Hermitian conjugate. The Hermitian conjugate has nothing to do with Rindler or anything. In any expansion, if you write it down, you always have to write down plus Hermitian conjugate. That's just a statement that phi dagger is equal to phi. So that's always true. Okay. But these CIHI modes are modes which have support in the future horizon, and they won't be of so much interest to us.
This 1/r follow-up is also.
That's just from spherical waves. It's just a fact. By the way, this 1/r follow-up comes from the fact that if you look at waves which go up to future null infinity, they are waves that have the form e to the I k r by r, the spherical waves, and then you add to it, some additional frequency, and that r plus t and r minus t is what becomes the affine parameters along past null infinity and past future null infinity. Okay, and then you have the 1 over r which I've kept. Does this
Does it have V out there or U?
this has u. Sorry, this is u actually. Sorry, so let me just specify. By the way, what I'm doing here is a sketch. Okay, there's no point in trying to make. Don't worry too much about these equations. What I'm trying to give you is an idea. And let me say once again that what I'm doing right now is I'm trying to give you an idea of Hawking's original derivation. Hawking's original derivation is not the most precise way to derive Hawking radiation. So I want you to get what the idea here is, not necessarily, get all the equations or even try to make all the equations. I mean, you're welcome to try it, you should try it. But it's not so important right now for us to make all the equations very precise. What will be important, and as you will see more, is for you to get what the idea of Hawking's original derivation is. In the second half of this lecture, I want to do something that's much more precise, and then you should make sure that all the factors are there. Right now, I'm just giving you an idea that there's initial data you can specify in the past and in the future, or the future horizon. And there are two expansions of the fields you can write down, and of course, these expansions of the fields have some Bogoliubov transformation between them. So the question is, find the Bogoliubov transformations. Yeah.
I still have troubles understanding what we are trying to do because we started with the solution. This solution is for the outside solution. I remember we had it for. It was a vacuum solution. But now we are introducing a field.
Correct.
And I also remember that when we introduced cosmological constant back in the day, it became an de Sitter space.
Yes.
So
this is a field which has only quantum fluctuations. I'm not going to give this field an excitation. You know, the whole point of doing quantum field theory in curved space-time is you have some solution, which is a gravitational solution, and then you're free to consider fields that have quantum fluctuations in top of it. Those fields which have quantum fluctuations lead to a gravitational back reaction, which will be important in what we do in principle. But the gravitational back reaction is suppressed by the Newton's constant, because the statement is that there's a field which has a quantum fluctuation which leads to a certain quantum energy density. And then that back reaction of that is suppressed by an additional factor of the Newton's constant, which is much smaller than the classical energy density that's present. So the whole idea of doing quantum fields in curved spacetime is that you have a solution. On top of the solution, you introduce fields which fluctuate quantum mechanically, and to leading order, you don't have to worry about how those fields correct the solution itself. At sub-leading order, when you introduce gravitational interactions, you have to worry about how those fields correct the solution, but that's not important at leading order.
Is there any a priori reason for not having any interest in CI?
No, it's a question of, you're interested physically in the question of what happens to an observer out at infinity. We can derive what will happen to a CI, we'll do it later. But what you're interested in physically is what happens to, at late time, to some observer sitting at infinity. So you could ask the question of what happens to an observer who crosses the horizon, and you could ask that question, but right now we're interested in Hawking radiation, which has to do with the fact that there's a thermal bath of particles out at future infinity.
And CI is not going to influence the future observation in any way?
CI doesn't, right? Because CI has support here.
Okay.
So there are some other modes which tell you what happens at future analysis. You're interested in the final stage of the black hole. What happens to a black hole after you've formed it and you're waiting for a long time and you're sitting in infinity? Okay, so is the setup clear? Is the physics of the setup clear? Okay. So now, the question is, what are the Bogoliubov transformations between A and BC? Now, there are two kinds of approaches you can follow. One of them would be to say, there's a complicated solution, we have this Oppenheimer-Snyder solution, let's actually do the calculation of the wave equation, and let's calculate the full S matrix, let's take these fields, AI, Fi, and evolve them through the Oppenheimer-Snyder solution, and let's see how they, reduce to fields in H plus and the future null infinity, and then that will give us the Bogoliubov coefficient. So it's a completely well-defined problem in principle, right? Given a particular solution, like the Oppenheimer-Snyder solution, you can take it, you can solve the wave equation, and you can solve this problem. So it's a completely well-defined solution. Given the Vaidya metric, you can take it, you can solve the problem, and you'll get a well-defined answer. If I give you the Oppenheimer-Snyder solution with some other initial density profile, you can take the wave equation in that background, you can solve it, and you will get an answer. Right? So it's a completely well-defined question. Okay? So it's a totally well-defined question. Given a particular solution, you can solve the question. Right? There's no question about that. Now, the Hawking's insight was to recognize that in fact the Bogoliubov coefficients between A and B do not depend on the details of the collapse. Okay? So the fundamental insight is that these Bogoliubov coefficients do not depend on details of collapse.
Basically, it depends on the geometry.
It depends on?
Geometry.
Well, the geometry depends on the details of collapse in some regions. This geometry depends on the details of the collapse, the geometry in these parts. But these particular Bogoliubov coefficients between A and B, this Bogoliubov coefficient at least does not depend on the details of the collapse. Okay? And it's given by something very simple. It in fact only depends on the mass of the thing that you collapse. Okay? So this is the fundamental insight, which is that there's one particular Bogoliubov coefficient which doesn't depend on the details of the collapse. Okay? So that's the result that you should. So by the way, I want you to get I would like everyone to get these two things. First, what is the question we are trying to answer? We have these two expansions for the fields. One is an expansion which is specified by giving initial data at past null infinity. Another is an expansion which is specified by giving initial data on the future horizon and at future null infinity. it's a well-defined problem in any geometry to find the Bogoliubov coefficients between those two. It involves solving the full wave equation and seeing what these Fi modes evolve to in the future. So it's a completely well-defined problem. And the result is that this Bogoliubov coefficient does not depend on the radials of the collapse. It only depends on the mass and on the angular momentum and some simple parameters. And what we'll do, we'll find it only depends on the mass. Okay? So this is the result, and I'd like everyone to get the framing of the problem and the essence of the result clear.
Going from data on I plus and H plus to data on I minus, like evolving backwards in
That's
time won't be so
You
well
can
defined.
do that also. That's also well defined. These are both Cauchy surfaces. It's a completely reversible problem at this point. It's just a question of solving the wave equation. At this point, everything is totally reversible. Okay, is this clear to everyone? The problem and the essence of the solution. Okay, now I'm going to tell you how Hawking derived this. Yeah.
It's not quite reversible, right? Because then you will have psi minus union H plus or H minus.
No, this is one Cauchy surface.
Right.
It gives you Cauchy data for the whole thing.
Yes.
This is another Cauchy surface.
Yes. But if
You
you
know,
are reversing it, it's
you see, it's like saying that you can specify data.
okay.
You can specify data on some surface like this, or you can specify data on some surface like this, right? That's what this surface is doing. I mean, is this clear? Why you can specify data on either surface? Yes. Okay. So what was Hawking's original point? What was Hawking's point? How did Hawking do it? So now I'm going to tell you how Hawking did it. The analysis, the way Hawking did it is a geometric optics analysis, and it's like subtle. So if you don't get the details, don't worry, but try and get the flavor of what Hawking did. The idea that he had was as follows. He said that look at, let's try and solve this problem in some approximation. And it turns out that the approximation is actually good for the essential things that we want. He said, think of waves that are emerging out at you. Okay. The waves that have initial data on this future null infinity, where do they come from at past null infinity? Right? So to first approximation, we can do a ray optics thing. Remember, I said sometime in the second lecture or something that if you look at the massless wave equation, it propagates along light rays. Right? So solutions to the wave equation can also be guessed by looking at ray optics. If you want to determine the point of constant phase, right? If you want to determine the trajectories of constant phase, those trajectories can be determined just by doing ray optics, just by drawing light rays. Remember, at some point we had a discussion about how the retarded propagator was delta of lambda. So you should remember, it was a tutorial question, which I hope all of you did. If you didn't, go back and do it. Okay, remember that the retarded propagator is delta of lambda. It tells you that solutions to the massless wave equation propagate along light rays. So what Hawking said was, look at this, look at light rays that come from here and go here. Which are the light rays that do that? Here is one. The horizon itself is one. Okay? The horizon involves a ray of light that starts at past null infinity, that's collapsing. You see, remember this figure, at every point in this figure you have an S2. Every point in this figure you have a sphere. So this is only an RT figure. So this is a ray of light which is very large in the far past, and it's collapsing. At this point, this ray of light has become of zero size. Once a spherical wave becomes of zero size, it crosses through and it starts expanding again, right? If you take a beam of light and you let it collapse to a point, and then everything will cross and it will start expanding once again, right? So that's why these rays bounce off the origin. If you take a spherical wave, they collapse and then they start expanding again. But this poor ray, it collapsed, and then by the time it started expanding again, it finds that it's trapped by the event horizon. So it can't actually get out to future null infinity, right? So this ray comes in from freedom and infinity, and it can't get out. It's jailed by the event horizon. Okay, so this is the last ray. This ray is called the last ray, which is the event horizon, or the ray that's just outside the event horizon. Okay, so there's a last ray. What about rays that go after that? These rays, this ray at least is living at the event horizon. These rays which go after that, we draw them in a different color. These rays go here. They're the same thing, right? Here they're passing through. They see a shell of matter. The shell of matter is pretty dilute at this point. It's just some dilute gas. these rays are collapsing, they go through the dilute gas, and they don't think that anything serious has happened, they bounce off infinity, but now they can't get out of this place at all, so they end their life in the singularity. Which are the rays that come out here? The rays that come out here, okay, are rays that go just before the last ray. Right? Rays that go just before the last ray, which are these rays in pink, maybe rays in white. These rays, right? These are the rays that give rise to initial data on you. This is the white ray, right? So there's the white, the green, and the whatever ray, the violet ray. Right? The violet ray is gone off into the singularity because it came too late from past null infinity. The white ray has bounced off the origin. When you say bounce off the origin, the physics is this, right? The ray collapses to a point and it expands again. That's what spherical waves do. It's bounced off the origin and it's gone off to future null infinity. And this green ray, which is the event horizon, is the last ray. Any ray that comes after that, ends its life in the singularity. Okay? So, Hawking said that these rays, okay, which come at future null infinity, are the rays which had support on this part. So if you look at initial data on this part before this last ray, that initial data is the initial data that propagates out to future null infinity in the geometric optics approximation. Now why is geometric optics a good approximation? In general, you might have thought that geometric optics is okay because that's how rays propagate, but something more complicated happens when you solve the full wave equation. But you might have thought that things spread, and I said this the other day also, that if you look at the wave equation in exactly flat space, things propagate along exactly right rays, but otherwise if you have curvature and so on, things will spread. And things spread inside the and so things, you might have thought that when it interacts with this matter, things would spread, and those interactions would be something very complicated. The essential physical point is that if you look at these rays which are ending up here are coming from a very small region here. We'll calculate the size of this region in a second. But the rays that populate all of this data, in the end, if you compute how much region of the affine parameter they come from here, you'll find that these rays are coming from a very blue shifted part here. If you have a very small range of the affine parameter here, that by the ray tracing gives you a very large range of the affine parameter on top. We'll do the calculation in a second. Therefore, these rays are very blue shifted rays. So they're rays which are extremely short wavelength rays. So Hawking argued that these rays will therefore not be affected by interaction with the stellar matter. Okay, they're rays that are traveling at extremely high energy, and therefore they'll just pass through the matter, and they won't be affected by the fact that there's curvature or there are other things that are happening. Okay, there is some curvature which the matter is causing, right? But that curvature is on long distance scales. If you have a very short distance wave, for that very short distance wave, it looks like everything is flat space. And therefore he argued that the geometric optics approximation was a good approximation to calculate this process, to calculate what happens to rays that are at least just around the last ray. Okay, so there are a lot of conceptual things, so I'll say it once again. You see, the thing is that the problem we want to solve is the Bogoliubov coefficient, and Hawking found an ingenious way to solve the problem, which was to solve the problem using geometric optics. The geometric optics approximation says that if you have some point of constant phase, it basically propagates to another point of constant phase along light rays. Okay? That's what things of constant phase do. Look at a wavefront of constant phase, it propagates along light rays to other wavefronts along of constant phase. Right? And he said, let's do ray tracing in this geometry, and we find that there's the last ray. There are rays which come after the last ray, which all end up in the singularity. There are rays which come before the last ray, which all end up at future null infinity. Okay, using that, we can determine how the initial data here propagates to how the initial data in the future, using geometric optics. Second, he said, why is geometric optics a good approximation? Because you find that the initial data in the future comes from a very small amount of the affine parameter here, so there's a big blue shift. And if there's a big blue shift, then these wavelengths are very short wavelength modes. They become long wavelength, once they come out, they get red shifted again, once they're climbing out of the black hole horizon. But they're very long wavelength while they're interacting, very short wavelength when they're interacting with the star. And therefore, it turns out that you can use the geometric optics approximation. So that's the physical justification for using it. Okay? Okay. So now let me draw this whole thing in another figure, and you'll see, how to solve this problem. So now we have to, of course, determine, if something starts here, where does it end up here? We have to actually do the ray tracing problem. But I hope the essence of what we are trying to do is clear to everyone. Okay, is the essence of what we are trying to do? It's an ingenious solution because you're solving what looks like a very complicated mathematical problem. The naive guess would have been to think, there is some particle creation by black holes, obviously, but it's a very complicated mathematical problem. Because you have this very complicated Oppenheimer-Snyder solution, and there are so many other solutions people have written down. You can write down some Vaidia metric, you can write down some other way in which things are formed from collapse, and you might have thought that this question is a very hard question. It's well defined, but it's very hard, and it depends on details of the collapse. Okay, the key insight, and it's a rather remarkable insight, is to realize that you can use this geometric optics approximation, which is justified because of this blue shift, and it will tell you, as you will see now, that things do not depend on the details of the collapse. So it's an important, seminal physical insight, which now we can see in retrospect. And so I'd like all of you to get this physical insight.
This will also depend on when the blue shift happens. If the blue shift happens after it emerges out of the shell, then it won't matter.
No, the blue shift has to happen here when it's interacting with the shell. When it's interacting with the shell, it needs to be in a short wavelength, which it will be. We will check. Right? Okay, good. So now I'm going to draw the same thing on a different figure. Remember, at some point we drew a figure of x versus t for the Oppenheimer-Snyder collapse. Okay? So I'll draw this thing on that figure, and I'll give you a sense of how this is calculated. Okay, so here's now the origin of radial coordinates, again r equals to 0. Let me use the same colors if I can. Here's the r equal to 0 line. Now we have this collapsing shell of matter. What did the collapsing shell of matter do in these coordinates? What it did in these coordinates was it started off with some finite, so I'm drawing a graph of not quite x. I'll draw a graph of x versus. So this collapsing shell of matter had the property it did this. Okay. So on the x-axis we have this coordinate called x, which is the radius of the S2, remember? So this tells you the physical size of the shell. Okay, it's not the R, on this axis we're not plotting what we call the R coordinate in Oppenheimer-Snyder. So I'd like to encourage you to go back and look at that solution. But what we are plotting here is, what happens to the size of the shell? And what happens to the size of the shell is very simple. The size of the shell starts at some finite amount. After some time it collapses, it reaches 0 and then it stays at 0. And so this is the trajectory of the outside of the shell. Right? Okay. Where is the event horizon? The event horizon in these coordinates is somewhere here. So this is 2m. Right? This is where the radius of the sphere is 2m. Okay? Okay. Now, what are these light rays and what are they doing? These light rays are light rays that come in from the past. So let's look at the white ray. It's some ray that comes in from the past. It's some ray that does this. Okay. It goes out here. Right? And then it gets stuck here for a long time. Sorry, this is wrong. Sorry. Let me move the shell a little bit. Sorry, just one thing. Let me just complete this figure and I will answer questions in a second. Someone had a question, right? Someone have a question? So I'm going to move the shell a little bit and do it too far down. here's my. Okay, so this, this shell, these are things which, which come from here. Okay? They bounce off the origin of polar coordinates. There are rays which come here that bounce off the origin, origin, do this, and then, they get stuck here for some time. In fact, I'll let draw it emerging. Maybe I'll draw it from this side. So here's this side. Okay, so sorry for my drawing things, I couldn't get space right on the board. So look at this ray. This white ray is something that comes from here. It comes from past infinity. So this is a ray, right? It's coming in here. It's bouncing off r equal to 0. Bouncing off r equal to 0. Now while it is still inside the shell, it has already exited this point r equal to 2m. While it's still inside the shell. Okay? So at this point, this is not quite a trapped surface yet. This is where the event horizon will be eventually, right? But if you're inside the shell, some of the shell is still outside. So the gravitational force is not quite enough to trap you to 2m. And so it's already escaped from 2m before the shell has reached here, and then it exits the shell. So what happens once it exits the shell? Once it exits the shell, then it's seeing a Schwarz shell geometry. Okay? And it finds that it's very close to where the event horizon is. So it's very close to a trapped surface. So now it's seeing a Schwarz shell geometry, it's very close to a trapped surface, and therefore it can't now expand too much. See, while it was inside the shell, it was happily expanding because most of the mass of the shell was outside, so it was expanding. Once it's crossed the shell, it finds that it can't expand too much, and so it stays stuck here for a long time. It's climbing out very slowly. It does climb out after some time because it's expanding slowly, but it expands very slowly, then it climbs out and then it goes off to infinity. Okay? There are other light rays that have the property that, they come much after this. So there is the green light ray, which is this ray. So the green light ray is this one. This ray is some ray that comes slightly after the white ray, okay, that's behind here. It bounces off the origin. It exits the shell just as the shell is at r equal to 2m. Just as it exits the shell, it's exactly at r equal to 2m. So actually it can't go any further, it just stays stuck in the event horizon forever. Okay? Now what about, some other shell, some other ray after this? Any other ray after this will actually fall into a singularity, it won't be able to emerge at all. Okay? A ray much before this, if you have some ray which is much before this, a blue ray here, and this ray will just escape, right? This ray will emerge here and this is basically flat space, so it just goes off. It gets stuck for a small time, but then it goes off. Okay? And there are many rays between the blue and the white and the green ray. I mean, there's some ray here, which comes here. Right? It stays stuck for a shorter time and then it goes off. Okay? So this is the qualitative behavior of light rays in a collapsing star. Okay? Now, let me tell you some other things about the result, and then I'll, or maybe actually. Let me show you this before. So, by the way, I want to say I'm not making this up, okay? Because it's a well-defined problem. So I'm not making this up, so you can check that I'm not making this up. There's a Mathematica file which I will upload today, okay? But let me show you. So we have an Oppenheimer-Snyder geometry. You don't have to believe anything I'm saying, right? It's just a question of solving geodesics, null geodesics in a collapsing geometry, right? So it's a well-defined problem. I'm telling you what the answer is, but in principle, all of you can go back and can check if what I'm saying is the correct answer or not. Okay? So let's look at the Oppenheimer-Snyder geometry. The details of this Mathematica file and the notes. So I'm not going to go through the details right now. I'm just going to show you what the results are. So the result is basically that you define. You have to define. You have to make a change of coordinates to these x coordinates that you can see. X is the radius of the sphere. It's the x that we have here. You have to change from r to x, and the change from r to x. Now r, remember, was Oppenheimer-Snyder was some point here, which was which told you the world line of a particle, which was sitting at some constant thing. So R doesn't correspond to the size of the sphere. The surface of the star was R equal to constant. You remember this? If you don't go back and look at it, we were using some coordinate system in which what we were calling R didn't correspond to the size of the sphere. The size of the sphere corresponds to this x. So you have to make a coordinate change, and then there's some thing of solving null geodesics in that, which is a simple thing. There's some technical issues in how you write down the equations, which are not important. Go back and look at the Mathematica file. I'll upload it and play around with it. But in the end, let me just show you the results that you get. These are the results that you get for geodesics in this. Okay, this blue line is the surface of the star. Okay, so this is the line which is going here, which is the surface of the star. So by the way, this is this has x on this coordinate and t on this coordinate. So it's a 90-degree rotation of that curve. Okay, because it's x versus t. The x is in the y-axis, so it's a 90-degree rotation. This is the line that's the surface of the star. So it's coming in, it's hitting 0, and then it's t at 0. This is the surface of the star. Okay? This is the past of all of these light rays. Okay? So these light rays are actually light rays which are separated by, I've exaggerated the amount they are separated by in the past in this figure. In this figure, they are all coming from almost the same point in the past. Okay? Then they come in, they bounce off the origin. This is this point, right? They bounce off the origin, and they exit the shell almost at the same point, but not quite at the same point. But then they separate a lot depending on where they exited. This green line is a green line there, it's the event horizon. It's a ray that stays stuck at r equal to 2l. Then there are some rays that escape. You can see they spend a lot of time here and then they escape. Right? And there are some rays that escape faster, and there are some rays that escape even faster. And you can see that this effect is rather sensitive. How fast they escape is very sensitive to the initial data. In fact, on this curve, you can't even make out the difference in these rays in the past, right? But you can still make out how they separate in the future. So you give them a small separation in the past, and they get a big separation in the future. That is the blue shift that we were referring to. You separate them by a small amount in past null infinity, which you can't even see on this curve, and they get separated by a big amount in future null infinity. Right? The RT trajectories diverge a lot in future null infinity. So it's a concrete mathematical problem which you can solve. This is the solution. Go look at the Mathematica file and you can solve it. Okay, so this is the qualitative aspect of the solution. Okay, so is this clear? Okay, that's all I wanted to show. I'm now going to switch this off. And I'll just tell you some facts of the solution, all of which, and I want to emphasize that I'm going to make a number of statements here. And what I want to emphasize by showing this is that even though some of these statements might seem ill-motivated, they're all based on very simple calculations that you can check in any given geometry. Okay? So I'm going to tell you what the results are, and if you don't believe them, you should just check. Okay. So now let me tell you what the results are. The results are as follows. Inside the shell, once they're inside the shell, okay, these rays basically propagate at move with delta x is equal to delta tau. Once they're inside the shell, in this region and in this region, they basically propagate, so they're covering equal distances in terms of radius in equal tau. This is true on this part of the trajectory, and this is true on this part of the trajectory where they bounce off as well. This is the statement that once you're inside the shell, once you're even slightly inside the shell, things look a lot like they look in flat space. This is what happens in flat space, right? The light rays go along delta r equals delta tau. I'm just using x because we have notation x here. Right? So this is what happens in flat space. So once you're slightly inside the shell, then things start moving basically along these kinds of trajectories. Once you're outside the shell, then we actually know what geodesic motion is. Okay? Then geodesic motion is along delta r star, where r star is the tortoise coordinate, right, is equal to delta t, where t is a Schwarzschild coordinate. This is different from tau and this is different from x. Okay? Both of these are different. T is the Schwarzschild coordinate outside, and r star is the tortoise coordinate outside, whereas this tau is the proper time coordinate inside the shell. And there's some matching between these two coordinates on the surface of the shell. Okay? So this is the trajectory of geodesic outside. This is the trajectory of geodesic inside. Okay, so I'm going to tell you what the result is, and I'll motivate the result. And it may not be immediately obvious why what I'm saying is correct. In fact, it's a tricky thing. So you should think about it more, or look at the Mathematica file. But what I'm saying is correct right now. So you see that. Think of the last ray, and let's look at this blue ray, for example. Okay, so there's some last ray and there's a blue ray. So this difference, let me call this time, this tau, let me call it V naught, okay, which is the V naught here. Okay, so as this ray propagates out, then you can check that this tau becomes the asymptotic time. So it preserves its value of V naught. So V naught is, remember, in these coordinates also, V is equal to U is equal to, okay. So you can check that in these coordinates, which, that is V naught. Okay. So it preserves, T plus R. At this point, T plus R is by definition V naught because R is 0. The radius of the S2 is 0. Okay. Therefore, this goes back and hits past null infinity. This ray goes back and hits past null infinity at a point V naught. That's in this figure. That's the labeling here of V naught. Okay. Now, what about this white ray here? What's the V value of this white ray here? You see, the V value of this white ray here is determined by two things. It's basically a question of how much before this green ray does this white ray hit this origin, which is x equal to 0. Okay. How much before does it hit the origin? Well, it's a question of, how much before does it enter here? Right? And then how much more distance does it have to travel? So this is actually only determined by, this is our, let me call this R. I'm just doing ray tracing, okay? So try to get a sense of what I'm saying. If you don't follow the details, again, don't be worried. What I'm saying here is simple. If you go back and look at it, you will see it. And I'll tell you, and I think it will help you if you go back and look at it. But don't get worried if you're not following all the geometric details. But they're not complicated. So if you try to follow, you will be able to follow. Just notice that the point at which this enters, let's call this R in. Okay. Then the time it takes to come here, let's call this let's call this X in. Call this R X in. And let's call this tau.
Are we considering the white ray or the green?
The white ray. The green ray already considered. Now I'm considering the white ray. The green ray is at V naught. That's some origin of coordinates which is V naught. Now I'm going to consider the white ray. The white ray enters the shell at some value tau. Yes, some value, proper time value tau, and at some radius of the sphere being x in, just being intersection point of the white ray with the radius of the sphere. Okay. If it does that, then when does it propagate here? When does it reach here? What's this point? If I tell you that this is x in tau, what's this point? In terms of, this is x in equal to 0, this is x equal to 0, and what is it in terms of tau? Exactly, it's just tau minus x in, right? It took x in back to travel here, right? And this is the v value, it's tau minus x in, because x is equal to 0 here. So the v value of this is tau minus x in. What is tau in terms of this? Right? So let's say we say x in is, so you can also calculate actually what this difference in tau is. Okay? You can check that if the, basically this tau is telling you how much time it takes for the shell to go from here to here. There's a velocity of the shell in these proper coordinates, which is telling you how much time it takes for the shell to go from here to here. Right? So you can check that this v coordinate is equal to v0 minus where this is the inverse velocity of the shell. You can guess, obviously there's a tau minus x in. So if tau was equal to tau naught, if tau was equal to this point, then this would just be, v naught minus x in, right? Because it had minus x in minus 2m, because the additional distance the white ray has to travel with the green ray is some additional radius which is x int minus 2m. Right? So if this time was the same as this time, then it would be x int just v naught minus x int minus 2m. But this time is also slightly different, and that's controlled by this inverse velocity, which is some constant. And therefore you can see that this v coordinate is v naught minus 1 plus alpha into x int minus 2m. Is this clear? Okay. Okay. How does this process look from the outside? On the outside, this ray is traveling along some point which is preserving a constant t minus r star. Okay. So this white ray outside is traveling on u is equal to t minus r star. Now what is t? T is not tau and r star is so what is t? So the way to calculate t is to think of this point as the intersection, is to view this whole process from the point of view of an outside observer. Okay? And then you see that if you call this v coordinate, I'm going to introduce a third v coordinate, which is the pink v coordinate, the v coordinate of the shell here. So if you call this coordinate vs, right? Then we have, and this is the U ray. Then we find that the intersection of the white ray with this coordinate, this is just given by t plus r star. Therefore, what's r star given by? So I'm just going to spend 5 minutes on this and then maybe we'll stop. Coordinate of the shell is seen from afar, okay, when it's crossing the horizon. If I tell you what's the v coordinate when it's crossing the horizon from afar, then you can solve for the u coordinate in terms of vs and r star, right? Okay. Now, what's r star? R star, we have a formula for r star. Near the horizon, what's r star? R star is just twice m plus twice m into log of x int minus 2m by 2m. This is the formula for r star in terms of x int. Remember, this x int is the radius of the sphere. Everyone agrees on that. That's some invariant quantity, right? So this, you can check, is just 2m plus 2m into log of v minus v naught by 2m into 1 plus alpha. Okay? And therefore, the relation between u and v of the rays is given by u ray is equal to some vs minus 4m plus 4m log of v minus, which is v naught minus v by twice m into 1 plus alpha. This is an irrelevant constant. This is an irrelevant constant because actually you can absorb it. This is a very relevant constant. Okay, so this is a relevant constant. Okay, these are constants you can absorb into definitions of the shifting the origin of u. Right? This Vs minus 4m is just a question of how you define the origin of u at future null infinity. That's some irrelevant thing of who defines the origin in what way. This is some other thing which you can shift the same way into redefining the origin of u. This, however, you can't. Okay, it's something that multiplies the relation between before and after. So you see that the central ray tracing result, for those of you who didn't follow the ray tracing derivation, this is the result. Okay, so just understand the result. even if you didn't understand the derivation, understand the result. The result is that you start with some point on past null infinity, which is V just before V naught. So, I'm sorry, I erased the Penrose diagram, but on your Penrose diagram you will see V naught. V naught is the V coordinate of the last ray at past null infinity. V is the V coordinate of the ray we are considering at past null infinity. V is smaller than V naught, right? Because the ray has to go before the last ray, otherwise it will never escape. So it only makes sense if V is smaller than V naught. If V is smaller than V naught, then the U at which it emerges at future null infinity is given by this formula. And the important constant here is the 4m into log of V naught minus V. The reason there is a log of V naught minus V is what tells you why there is a divergence. If V is very close to V naught, if you have two V's, both of which are very close to V naught, the U's will be very different. Right? The U's will be very different, and that's what tells you that you start with geodesics at almost the same value of V, yet they diverge at late times. The U values become different. This is what explains what was happening in that figure. Okay? Actually, maybe I should keep the figure on. It would help. Actually, I don't even have to erase the figure. Right.
How did we get that relation? V equals tau minus x equals V0 minus 1 plus alpha.
How did we get what result? Which one?
V is V0 minus 1 plus alpha.
This one, you see, this is tau, this is the definition of tau. So this point, which is the V coordinate when it comes out, is tau minus xn because it travels along delta xn equal to delta tau.
That is fine for the next one.
So you see, what is xn? If xn is almost 2m, right? It's a little different from 2m. So there are two things that are different between this ray and this ray. One is that this tau is slightly smaller than this tau naught. Right? How much smaller? It's a question of xn minus 2m divided by alpha, where alpha is the velocity of the shell. So it's a question of how much time went in here. And it's a question of how much went in here. So you have to add these two, right? Because the additional V is a sum of this part and this part. So one of these parts is alpha into xn minus 2m. The other of these parts is just xn minus 2m. That's what these things are. Okay? The 1 plus alpha in any case, as I'm now saying, is irrelevant. What's relevant is the constant up front, the 4m. So you can see that's what's happening here. You start with rays which have almost the same V. One of them is at V naught, so it gets stuck. In fact, it never reaches out to U. Right? The other rays are slightly different from V naught, and because of this logarithmic factor, they deviate. Okay? So this is the result. You can check it by this, or you can check it using Mathematica. You can check it in many ways, but this is the result. Okay? Okay. Are there any questions? So now I'll just write down the answer for Hawking radiation. You see, now we have come back to a situation which we have seen now twice before, which is a situation where we have these two rays, we have these two expansions. One of them is phi out. I think, what did I call this? Did I call it E? What did I call the outgoing modes? I know U was there, but was it E? I have something different in my notes here, so I don't know what I call them on the board right now. B? Okay, B. So let's call them B. Okay. If you look at the lecture notes, I should only have used A and B differently, so don't get confused. I'm using something different on the board. This is the outgoing expansion, this is the ingoing expansion. This is A. And crucially, we have said that when the phase of the field is something on the V coordinate, that same phase is propagated to some phase of the U coordinate where the U and V are related in this form. Okay? So these two expansions are the same. And note that in these expansions, U and V a priori refer to two different points of space. Okay? So we don't have we shouldn't just equate these two expansions. One of them is a function of V, the other is a function of U. And this is a function of V, this is a function of U. These are two different coordinates. But the ray tracing is telling us that we can, and it's telling us how we should equate them. It's telling us we should equate them by putting this relation between u and v, right? This logarithmic relation. That's the point of ray tracing, is telling us how you should equate coordinates at future null infinity with coordinates at past null infinity. Okay? So is this clear?
The
Okay.
ingoing one will be characterized by u, right?
What one?
The ingoing fields will be characterized.
Ingoing are v. The outgoing are u. V is the coordinate of the past null infinity. U is the coordinate of the future null infinity. The horizon is that u equals 0 in R. Okay? Okay. So now we have once again a situation where we have two expansions in two different coordinate systems, and the coordinate systems are related by a logarithmic or an exponential term depending on which way you look at it, right? So you see, once again you have the same 4m log which we have now dealt with twice. Okay? So without even doing too much additional work, you know the Bogoliubov coefficients between the a's and the b's are the statements that we don't have to do the same calculation again. We've reduced everything back to a logarithmic thing. Okay? If you look at the A vacuum, it satisfies mixed state for B with a density matrix. So what is beta? Can you look at that coefficient and tell me what beta is? Yeah, what's beta? You've seen this before. You've seen this exponential relation before. Right, it's 8 pi. Okay. And this 8 pi comes from taking that 4m and multiplying it with the 2 pi. Okay, which is what we derived. When you had an e to the minus AR relation, the temperature was 2 pi by A. And you can see that. Okay. Okay. So this completes our derivation of Hawking radiation. By the way, why does it look like a mixed state for these rays outside? What happened? How has it become mixed if you started with a pure state? What are the things entangled with? What they entangled with are the modes inside. You see, they are entangled. These rays, this data is entangled with rays which never make it outside. So these rays, you see, if you look at data on past null infinity, which is data up there, let me draw it here once again. You see, these rays, which is the last ray, this is at V0, this data is entangled with this data. So these rays, which are these rays, are entangled with information behind the horizon. So there is entanglement across the horizon. So these white rays, which are the ones we have calculated, for which we are claiming there is a density matrix, are entangled with things behind the horizon. Okay? So white is entangled with violet. In this picture. And where does the violet come from? The violet comes from here. And the white comes from here. So there is entanglement, in the vacuum at past null infinity. You should realize that the vacuum itself has entanglement between different parts of space. In the vacuum, even though it's a vacuum, if you think of it in terms of mode excitation, one part of space is entangled with another part. In fact, that's why you have non-zero correlation functions in the vacuum. So in the vacuum at past null infinity, this part before the last ray is entangled with the part after the last ray, which translates into, here, into entanglement of this with this. Okay? Okay, someone asked a question about what about the modes which have data here, these modes which have data here. These modes which have data here are just the modes which come after this part. Right? So if you set this to be in the vacuum, these modes will also be in the vacuum. The modes which have data on the future horizon are just the modes which come after the last ray. Okay? That's what these C modes are.
So
these violet rays are also part of the C modes because they're this part of the C modes, part of the C modes.
But you can't observe it.
Huh?
But you can't observe it.
Well, they're behind your horizon. They're not visible at late times. At late times they're behind your horizon. Okay, so does this completes the derivation of Hawking radiation. What is it that I want to emphasize? And I'm now going to go through in about the remaining 20 minutes what I think is the most precise derivation. What is it that we, yeah?
How do you make precise the statement that the vacuum is entangled?
The way you make precise the statement, you can write down the vacuum in terms of the field. Have you ever seen this expansion of the vacuum state in field theory in terms of a wave functional over the fields? Maybe we can discuss in the tutorials that why is it that the vacuum has entanglement between. The fact it has correlations between different parts tells you there's entanglement. But maybe we can discuss in the tutorials why vacuum is entanglement. Okay, good. So by the way, let's see, I had some tutorial questions maybe. Okay. So the main tutorial thing to do right now actually would be for you to look at this Mathematica file and persuade yourself that whatever I said about the solutions of the geodesics is indeed true in the Oppenheimer-Snyder collapse. Okay. It's also true more generally. The advantage of our derivation is we didn't have to use a specific metric, but you do have a specific solution, so you can check if in that solution things are true or not. So now I want to move on to the most precise, what I think is the most precise derivation of Hawking radiation. We've done two derivations. One of them involved, using the Unruh effect and then using the fact that the horizon is locally like a Rindler horizon. The other was the original derivation, which gives you a more physical sense of what is happening. It tells you that these modes that are being produced by rays which start in the far past and they are empty, but somehow they get populated by passing through the horizon. And the calculation of that is rather simple, and it follows from this ray tracing approximation. It's kind of a like this one.
So the Bogoliubov coefficients are not really transmitted.
They have been, because you see we know the coordinate transmission. It's the same, determining the Bogoliubov coefficients is doing the same thing that we did before. Given two coordinate systems and modes in two coordinate systems which are related exponentially, how are they related? So we already did that problem. If I give you the modes and I tell you that the modes, once I give you the modes, that totally determines the Bogoliubov coefficient. Right? So I have told you what the modes are.
But it's a complicated exponential.
Yeah, the Bogoliubov coefficients are the same coefficients we have for Rindler. That we have. Okay, good. Now, yeah.
What is it that makes this derivation precise? The geometrical optics approximation?
Yeah, it's I don't know. I'll give you a derivation now, and you can see it's more precise. It'll tell you also the limitations of this equation. It's a geometric optics approximation. It's the fact that at various So that's one. As you can see, we were making arguments that were plausible about how these geodesics behave, but doing a much more controlled thing and showing that that's how it is in all sorts of solutions is much more complicated. So there's what are the error terms here is much harder to control. This is correct up to what order? When does it fail? Is much harder to control. What I'll show you now, you can take note. Okay, so what is the key point? The key point now is to look at correlation functions of the field. Okay, and just by looking at correlation functions of the field, we will derive what the relation between these modes is. So I'm going to make the following universal state. I want to look at correlation functions of this kind. What state, when I talk about these correlation functions, what is the state in which I'm computing them? I'm going to compute them in whatever state is obtained by forming the collapse of the black hole. And in fact, I'll use these correlation functions to define some properties of the state. So I'll put a condition of these which specifies, which will actually help in specifying what this state is. So what's the condition that we're going to put? These U1, U2 are the, and let me put an X coordinate also. What are these U1, U2? This U1 and V1s are the same U1s and V1s we've been using so far. Okay, it's the R star plus T and R star minus T coordinates. What are these X coordinates? These X coordinates are the other coordinates, which you can think of as the coordinates of the sphere. Okay, so there are some other coordinates in the game, and the field depends on them as well in principle, and these are the other coordinates in the sphere. Okay, so I want to consider these correlations. What do we know about these correlation functions? Do we know something universal about these correlation functions? It turns out that we do. We know something universal about correlators of fields. If you look at free fields, we know that as you take this is 1. Actually, no, don't even need to take x1 going to x2. As x1 minus x2 squared goes to 0, as these fields come close to a light cone, you know what happens to position space correlators of fields?
Diverge.
They diverge, but in what way? Sorry, there's an x here which is the transverse x, and this x is now all coordinates. Okay, so don't get confused by notation. You know what this divergence is? What do position space correlators of free fields look like? No, they look like 1 by x squared in 4 dimensions. You know, the 1 by k squared transforms to 1 by x squared, and there's a delta function on the light cone, but right now I'm not taking them to be exactly on the light cone. So when they're near the light cone, if you look at these correlators, this is not the commutator, it's not the retarded range function, it's just a 2-point correlation function. You can check that this correlator has the form that it looks like x1 mu minus x2 mu, x1 mu minus x2 mu. Okay? It looks like 1 by x squared. Okay, as x1 minus x2 squared, as this term goes to 0, it diverges in a particular way. It diverges as you approach light cone. You can check this. One good place to check this is a very old book by Bogilyubov and Shirkov, which I think is actually a good book. Most quantum field theory textbooks don't even discuss position space correlators, although this one will be discussed. But I know one place where it's discussed in great detail is a book by Bogilyubov and Shirkov. But you will find it, I think, in more modern books also, or you can just derive it. So it's a fact about correlation functions. It's something that's true, in fact, regardless of what kind of interactions you have, as long as you're dealing with a theory that's asymptotically free. As you approach the light cone, the physics that dominates things is the physics at high energies. So even if the field is interacting or has some other properties, this property of the field only relies on the fact that it's asymptotically free. So this is a very general result. Okay? It's a very general result. There are some coefficients here, by the way, that I'm not dealing with. So they are proportional to. It depends on whether this is 1 or 2. It depends on how you normalize fields. So this is very general result. Okay. What does this tell us about correlation functions in a Schwarzschild black hole geometry? You see, if you're going to quantize fields about the Schwarzschild black hole solution, then it tells us that as we take correlators across the horizon, you can take this u1 and u2 to be at 2 points of the horizon, right? You can take u1 to be here. You can take a line of constant v, and you can take u2 to be here. So this is u1 v1, and this is u2 into v1 plus delta v. Right? So they are almost on the light cone, not quite on the light cone. Here's one point, here's another point. This is the line of constant v. So they are approaching the light cone, but they are on opposite sides of the horizon. They can be separated by some distance in the u coordinates. This is telling you something about these correlation functions. This result, telling you can separate things in the u coordinate, and as long as they are close to being on the light ray, there is a certain universal property of these correlation functions. Right? Okay, we can actually derive an even stronger result. The stronger result comes from looking at this. So what does that correlation function look like? So by the way, in the metric that we had, the metric looked like du dv into some 32m squared, right? So the metric in these uv coordinates looks like ds squared is equal to some k du dv minus dx squared. Okay? So it looks like some k, where this k is some 32m squared or something. Near the horizon, this is what the metric looks like. So it tells you that this coefficient function is what? 1. Right? Okay. Now I'm going to do something else, which makes the result even stronger, which is I'll differentiate this correlation function with u1 and with u2. Okay? So now I'll consider a slightly different correlator. When I differentiate this with u1, and differentiate this with u2. Okay, what happens if I differentiate with u1 and u2? Okay. What happens is I pull out some factors of, we just differentiate this with u1 and u2. It's both times it's like differentiating with delta u. Okay. So what happens? You get minus 2 e squared into delta v squared. And what happens to this exponent? We differentiate this twice, 1 by x twice. Becomes cube. So don't get lost. I'm not doing something very complicated. Okay, so you differentiate 1 by x twice, you get 1 by x cubed, right? So you differentiate this with respect to u1 and u2. You pull out 2 factors of delta v, 2 factors of k. You get this 2 because you had a 1 by x square. When you differentiate that, you get that, and then you get a cube, right? Everyone happy with that? Okay. Okay. Good. Now here's a statement. Take the limit of this guy. Take the limit as delta v goes to 0. Okay, the limit as delta v goes to 0 is given by delta 2 of x. X is a two-dimensional coordinate, right? Because x has 2 other dimensions left. A u, v, and then there are 2 other dimensions. It becomes delta 2 of x proportional to by delta u of delta u. Okay, this is a tutorial problem which I encourage you to do very strongly. Actually, the solution is in the notes. So even if you look at the solution and are then able to explain it on the board in the tutorial, that's fine. But I encourage you to do this, okay? Very strongly. You can prove that the limit of this guy, you see, you might have thought that this limit is 0 because there is delta v square in the numerator. Okay, but the limit is not 0. As you take delta v to 0, because there is a situation where you might have x equal to 0, and then there is a delta v cubed in the denominator. Okay, when you do this carefully, you can show that this limit is a delta function in the x with a delta u squared. Okay, so I strongly encourage you to attempt this problem. You can show it's true. This is telling you that as you look at this correlation function, and as you take the limit as u1 as v1 goes to v2 of this correlation function, it gets a very funny property. It picks up a delta function in x, right? This is limit is proportional to limit. There are some constants which we are not interested in. Del u1 phi of phi 1 means phi of u1 phi of v1, and del u2 phi. So this limit is proportional to a delta function in x. When I say delta 2, it's because it's delta x1, delta x2, right? X has 2 coordinates. And that's a very funny property. Usually, correlation functions are proportional sometimes to delta function in light cone distance. They are never proportional to product of delta functions in coordinates. It's a very unusual property. This delta function is what is sometimes called ultra-locality in light cone physics. Okay. This is what's called ultra-locality in light cone physics.
Shouldn't there be delta u1, delta u2 in that first line?
Shouldn't it be what? What?
You are differentiating with respect to del u1.
And del u2.
Yeah, and the denominator is just delta u.
Denominator has a delta u, that's right. So differentiate with once with u1 and once with u2.
There should be some factors dependent on u1 and u2.
No, it's u1 minus u2. Delta u is u1 minus u2. Oh, sorry.
Oh,
Sorry. I thought this was obvious. Delta u is u1 minus u2. Delta v is sorry, delta u is u1 minus u2. So, I should write delta x. Oh, sorry. Sorry. This delta is difference in the 2x coordinates, and yeah. Okay. Is a result clear? It's just a result about taking this result. So let me just take a step back. Actually, we won't need so much. Okay, we have 5 minutes left. You see, this result is a statement about what is the physics we are putting in. The physics we are putting in is a statement that fields are asymptotically free. The fields we're dealing with are asymptotically free. If they're asymptotically free, they have a certain fixed correlation function at light cone distance. That correlation function is given by this. This is a result, a physical result we're putting in. What's the second physical aspect we're putting in? The second physical aspect we're putting in is that the metric about the horizon is the metric that we calculated in the geometry. Okay, there isn't a large back reaction. Therefore, we know the metric, we know this G mu nu is near the horizon. What is the G mu nu? It's this. This is the G mu nu near the horizon. It's k du dv minus x squared. Okay. Therefore, if I put that result and I put it here, I get this. Then I differentiate. Why am I differentiating? Because it gives me a simple result. I differentiate once with u1, once with u2, I get something. And then to simplify even further, I take the limit of that derivative as delta v goes to 0. And I find a very simple result. I find that this correlation function becomes ultra-local in the transverse coordinates and has a factor of delta u squared. This, by the way, tells me also not only that things are ultra-local, but also that physics is effectively two-dimensional. Even though I started with a four-dimensional theory, in the transverse directions, everything is just becoming, everything just has to be fixed to have correlation functions. If you're at x1 at one point, you have to be at x1 at the other point. Okay? But in these u and v directions, there's something more interesting happening. You get some term here which is regular. This is something that happens in any number of dimensions. It's not fixed to 4 dimensions. If you have 10 transverse directions, the physics becomes ultra-local in all those 10 transverse directions.
Can you explain the terminology ultra-local again?
It's this. It means that you get the correlation function of phi1 at x1 and phi2 at x2 becomes proportional to a delta function x1 minus x2 multiplied with a delta function of x1 minus x2 in x coordinate and x1 minus x2 in y coordinate.
How is this different from usual correlation functions?
This is never what happens in usual correlation functions. You should check. Usual correlation functions, if you look at phi of x1, phi of x2, it never becomes delta 4 of x1 minus x2. Or it never even becomes, if you have coordinates x, y and z, you never get a delta of x1 minus x2 into a delta of y1 minus y2. Usual correlation functions never have this property. They just don't satisfy this property. Sometimes you might get a delta of e squared minus x squared minus, of some light cone distance. But you never get individual products of delta functions for the coordinates. What you're getting here is individual products of delta functions for the coordinates. So it's very different from what happens usually. It's something very special to a particular limit of correlation functions.
So these are coordinates of S2, right?
These are coordinates in S2. Or you get, these are coordinates in S2. You get alpha locality in those coordinates. That's it. Okay, now, good. So now, let's see what this implies. So let's try and reproduce this result, which is a general result we proved for. Let me just write down the full result once again. I'll just make it here, and we'll reproduce on the other board. We'll try to reproduce this result. Okay. So this is the final result which we should remember. I'll just write down the final result once. Is equal to huh? Oh, yeah. Okay, so this is the result we got.
This only depends on there being a null horizon, a null
This
surface.
actually depends on nothing. This is the result which just depends on that result.
Yeah.
And it depends on the fact that about the horizon the metric looked like du dv, that u and v were null coordinates. It only depends on the fact that u and v are null coordinates. So if I want to apply to the horizon, then it depends on that. But this is a statement that holds generally. It holds not only near the horizon, it holds everywhere. It holds outside, as long as u and v are null coordinates.
So this alpha locality is true for this left-hand side, right? So this
For this limit. It's not true for the correlation function. When I differentiate and I take this limit, it's delta v.
what is the significance?
It's a particular convenient limit. You're taking, you see what you're doing is you're taking 2 points and you're taking them to be very close in the light cone. So it's a light cone correlate. It's a correlator where, as delta v goes to 0, it means the v coordinates are almost approaching. They're almost on v equal to constant. So you're taking a correlation function like this. You have one point here, another point is very close to the light cone. And that's when physics becomes ultra-local. So light cone physics becomes ultra-local.
You also taken derivatives.
I have taken derivatives. The derivatives have to do with the fact that they have to do a slightly subtle fact. They have to do with the fact that if you because physics is becoming effectively two-dimensional. Massless fields and scalar fields in 2 dimensions aren't very well behaved. They have correlators that long distance behavior, some log of u1 minus u. The reason I've taken the derivative is because I'm dealing with scalar fields which are massless. I mean, being a massive or massless is not important in light cones. And because physics is becoming effectively two-dimensional, the scalar field itself is not a good operator in 2 dimensions, but the derivative of the scalar field is a good operator. So those of you who study two-dimensional theories know that the scalar field itself is not a good operator, but the derivative of the scalar field is a good operator. Okay. Good. Now, what do we have? Now I'm going to derive this from a mode expansion. So I'll take 5 minutes extra, but let's finish this and not push it to tomorrow, because then we can do the information paradox. So let's now quantize the field and try to derive this from a mode expansion. So actually we have almost all the tools we have in hand. Let's call this the horizon u equal to 0. Remember yesterday I said that you can quantize the field, I don't know if I use A or B or what, but you can quantize the field outside the horizon in this form. U to the minus I. I think it calls V yesterday for some reason, but I don't know why. That's K omega into E to the minus I. Conjugate. Okay. This is outside the horizon. What is this expansion? This is the expansion we wrote, which looks like E to the I omega R star minus T. Remember, this is just E to the I omega R star minus T. This u to the minus I beta omega, where beta is 8 pi m, is the same as E to the I omega R star minus T. Remember yesterday I said that near the horizon modes look like E to the I omega R star minus T at the end of yesterday's class? You remember we solved the wave equation yesterday at the end of, go look back in your notes, and the solution to the wave equation looks like E to the I omega R star minus T. It starts looking like d by dt square and d by dr star square. That written in Kruskal coordinates is u to the I minus I beta omega by 2 pi. Okay. Okay. Then I can similarly quantize, so this is the expansion outside. I can also quantize the field here, right, by introducing another Schwarzschild patch. So I'll get some correlation here. This is called D. These A's are the same as these A's because V is continuous across. Okay? But the U's are not continuous. So you'll get different modes for the U's. So this is A omega into V to the minus I beta omega by 2 pi. Omega plus V omega tilde by square root omega. Okay. Okay, so this is the mode expansion. It's right now I've just written some modes. I haven't done much, but you can check. I'm going to say that if you set this following correlation function, B omega tilde is equal to e to the minus beta omega by 2 to 1 minus e to the minus beta omega into delta of omega minus omega prime, if then the correlation function of the fields phi outside phi inside will have that result. Okay, I'm going to check this for you. So I'm telling you that this is what you need, and I'm going to check. I'm not deriving that this is what you need, but I'm going to check that if you impose this and you look at the correlation function of outside and inside, you will get that. Okay? Okay. So what happens as you look out? Sorry, I made a mistake of sign. Sorry, very important mistake of sign. Let me call this let me just make sure I'm consistent with my conventions. This is what I call in my notes U1, and this is what I call in my notes U2. Okay, so U2 is the one which is outside the horizon, and U1 is the one which is inside the horizon. This is a plus I beta. Why is it a plus I beta omega, by the way?
Left movers and
Right, actually we discussed this in the Rindler case. Remember, inside the R star is what becomes time. Once you're inside, it's the radius that's behaving like the time-like coordinate. So whether you have a creation and annihilation operator depends on whether the frequency is positive with respect to R star or T. And the U has an R star minus T. That's why this comes to the minus sign. This is an annihilation operator. This is a plus sign creation operator. Okay, very good. So now check if you impose that correlation function and you compute this guy. Okay, so some simple algebra to check. Now, the first thing is that you will see immediately. Oh, yeah, I'll try to emphasize. Sorry, I should emphasize here as well. There are some transverse coordinates that we are ignoring, which are actually there. Right? There's some behavior in the transverse coordinates. So I will check. This is e to the I k dot x2, and this is e to the I k dot x1. Right? So there's an omega, and there's also some behavior on the transverse coordinate. And remember, I said that becomes irrelevant, right, in the near horizon wave equation. If you look at the near horizon wave equation, the transverse coordinates drop out. Okay, you can check from the wave equation. Maybe we'll check again in the tutorial today. But if you solve the wave equation, you can check that you get a solution where this omega tells you the R star and T momenta have to be the same, but doesn't depend on the transverse momentum. Immediately you see from this expansion in near horizon that you get this delta of x1 minus x2. If you take these two modes and you look at the correlation function, you will immediately see that you will get this delta of x1 minus x2. Okay, because you will get e to the I k dot x1 minus e to the I k dot x2, and you will just get a delta function in them. So you will immediately get this. Okay. And sorry, just to make more precise, let me put k here, b omega k and b tilde omega k, right? Okay. So this delta function in the case will immediately give you that delta 2 of x1 minus x2. So you're immediately able to get this part by looking at this, by taking these expansions and putting them in, and using these correlation functions. Okay. Sorry. I have a feeling that people are getting lost. So you know what? Maybe rather than trying to complete this now, I'm happy to do some of this tomorrow. Why don't I stop here and see if there are questions? Are you following what I'm doing, or let me just recap. Okay? So as I said, this is slightly advanced material. The place you should, in fact, I don't know any textbook where this is done. Okay, so I'm going to tell you where you can. One place you can find this is in a paper that is in a very long paper we wrote, but I'll tell you the reference. Look at this paper by Kyriakos Papadimos and myself, which is archive 1503.0885, and look at section 4.1. Okay. Look at section 4.1. It has this derivation. Actually, I'll put up the full derivation in the notes. But since I have a feeling people are getting lost, so I'm going to help you by recapping once more. Okay. Once again, it's advanced material, so don't get worried if you're getting lost. I want you to get the flavor of what's happening, even if you're not following the details. You see, what we have done so far is what we're trying to do is we are trying to derive Hawking radiation by using some properties of correlation functions so that we can come up with a much more precise derivation. So far, what we've done is we've used analogies to derive something. You used an analogy with the Unruh effect to derive a result. And in the second case, we use this geometric optics thing to derive the Bogoliubov coefficient between the modes outside and the modes inside. Okay? But both of these clearly had some imprecisions. In one case, we used this geometric optics approximation. In the other case, we had some analogy of the Unruh effect with the horizon of the black hole. Okay? Now we want to see how we can get this derivation without going through any of these analogies. And so what we are trying to say is, we are trying to say that the existence, so what is the central point we are trying to make? First, we are saying that if the horizon is smooth and has the metric that you expect from this classical solution, then you know that fields across the horizon have to have certain correlation functions. Position space correlators across the horizon have to have a certain form. Right? That's just guaranteed by the fact that the horizon has a certain geometry. If position space correlators across the horizon have a certain form, then momentum space correlators also have to have a certain form, which is obtained by Fourier transforming those position space correlators. So if the correlators of the fields in position space have to have a certain form, which is dictated by universal properties of fields, asymptotically free fields in any smooth geometry, then by Fourier transforms, it tells you that the modes, the momentum space correlators or the mode correlators also have to have a certain 2-point function. Okay? So if the position space fields across the horizon have this correlator that we derived, then it tells you that the momentum space modes, the modes outside and the modes inside, have to be entangled in this thermal way. Okay? And also that the 2-point function of the modes outside in momentum space has to be of a certain form. So we are using properties of position space correlators to derive properties of momentum space correlators by doing a Fourier transform. Okay, so that will tell us what the 2-point functions of the modes outside and outside have to be, and outside, outside and inside have to be.
So if I calculate A and A, I mean, here you've got B and
A and A.
and
A
you've got
and
A.
Yeah.
So,
Yes.
I mean, shouldn't they also be complementary in some way?
Well,
You should say a thermal state in both cases.
good. So the fact, very good. So the A modes, these are modes actually that have, so writing down this expansion, I actually assumed a little more than assuming something in the future horizon. If this expansion has this form, these A modes are actually relevant when you try to cross the past horizon. See, these A modes, which go like V to the I omega, were derived under the assumption that the wave function has a certain form as R goes to R horizon. But actually, to get this full form, you also need to assume that there's a past horizon. Okay? If there's a past horizon, then it's true that the A modes are also entangled, but this is inside the future horizon. The A tildes are live inside the past horizon. Okay, so these A's, A tildes, B tildes are the same thing that occurred in Rindler space. But remember, in region 2 in Rindler space, the right movers from the left side came into being, and the left movers from the right side came in. So that's why inside the horizon you have the left movers from the right side, and the right movers from whatever the inside of the black hole is. And if you do have a past horizon, then you will also have the A tildes. If you don't have a past horizon, as you might not have in black holes from collapse, then there are no A tildes. The A's will not be excited. If you have a future horizon, the things that's relevant is the B's and the B tildes. Okay. So is it clear what we are trying to do? I'll complete the derivation tomorrow. I'll put it up anyway today so you can look at it. What we're trying to do is we are trying to use universal properties of position space correlators to derive the entanglement in frequency, which is what we want to derive. We want to derive that there's a thermal bath, and we're going to do it by Fourier transforming the position space correlator.
Where is the Rindler fireball in the Hawking derivation, geometry optics?
There's no, what do you mean Rindler fireball?
The fireball that came by crossing the horizon.
There's no fireball that came crossing. Sorry.
The horizon was irregular, right? One of the horizons were irregular in the
There the correlation function.
In the Rindler case, sorry, in the Rindler case there was no, I said that if you looked at the Rindler vacuum, then the horizon would have a fireball. But the collapsing black hole, we don't believe is in the Rindler vacuum. In the gravitational case, in that vacuum corresponds to something which has a very high energy particle living behind the horizon. We don't think that the collapsing black hole is in a fireball state. That was a statement about the Rindler vacuum. The collapsing black hole is in what's more like the Minkowski vacuum. It's in what's the vacuum for the information.
So there the correlation functions diverge, right?
Which correlation?
If you're calculating it between 1 and 2.
No, they don't diverge. The correlation functions will have this form. You see, the correlation functions, remember I said, are covariant. Correlation functions don't depend on which plane you calculate them. The first thing we said was correlation functions are covariant. This is a result that applies perfectly well to Minkowski space. It's a result that applies much more generally. It's a result that also applies to Minkowski space. If you take U1 and U2 to be in 1 and the other one to be in 2, this is a result that will hold. Correlation functions have this form in Rindler space as well.